Welcome everyone. For today's prep, I want to look at our general exponential rule. Try a couple examples. So we started looking at this in class and just want to kind of go over the idea here behind this special chain rule version specifically made for exponential functions. So what this general exponential rule says is if we have a composition where e is the outer function, so e to the x is the outer function, and g of x is the inner function, so it's the term inside the exponent, how we differentiate this thing, e raised to the power g of x, well, we use chain rule. So if we remember what chain rule said, when we have an outer function, we differentiate the outer function, we keep the inner part exactly the same, and then we multiply by the derivative of the inner function. So for us, when we differentiate the outer function e raised to the power x, that part just stays exactly the same. So the exponential part of our derivative stays exactly the same. And then we multiply by the derivative of the inner function, and in this case the inner function is the stuff in the exponent. So we're going to multiply by the derivative of the exponent terms. So this is our special exponential, general exponential rule. And let's try a couple examples. So I want to look at example 1, and we're just going to try a few of these. So let's look at the first one. We have the function y equals 5 e raised to the power 5x. So when we differentiate this, let's do our derivative. We're going to use the general exponential rule. So let's see how this is going to work. We'll call our derivative y prime. And when we differentiate, the exponential part stays exactly the same. So we're going to have e raised to the 5x. And then we take the exponent and we multiply by its derivative. So e to the 5x times the derivative of 5x. And if we finish that off, the derivative of 5x is just 5. So our derivative here would be e raised to the 5x times 5. And usually it's a good idea, take that term at the end and move it to the front. So it's easy to lose track of terms. I like to kind of put constants in front. So not really necessary, but it is helpful usually. So put the 5 in front. All right, so that's the idea. This is our general exponential rule. So the exponential part stays exactly the same, and then we're multiplying by the derivative of the exponent. So let's try it again. Let's try another one. So let's look at the function e raised to the x squared plus 1. So let's differentiate. So the function's called y, so let's call this derivative y prime. And again, the exponential part stays exactly the same. So it's going to stay e to the x squared plus 1. And then we take the x squared plus 1 and we multiply by its derivative. So what we're doing is we're differentiating the outer function, and for exponentials, it just stays exactly the same. And then we're multiplying by the derivative of the inner function. So this, in this case, the term in the exponent, so x squared plus 1. And when we differentiate, we finish differentiating, we have e to the x squared plus 1 times 2x. And again, usually a good idea, just move the 2x out in front. Okay. Let's try one more. So these are not too bad. Let's look at the last one here. Y equal to 3x squared, e raised to the 3x squared minus 1 over x. And we're going to do our derivative. Same thing, the function's called y, so we'll call it derivative y prime. And when we do this, again, it's an exponential, and then it's the exponent that has all the stuff going. So when we differentiate the outer function, the exponential part just stays exactly the same, just like e to the x. Derivative of e to the x, it just stays the same. Derivative of the outer part here just stays exactly the same. So that's what this is. But then we have all this stuff in the exponent. So we do have to differentiate that. So we multiply by the derivative of the terms in the exponent. And if we finish that off, now it's just regular power rule type stuff. So we end up with 3x squared minus 1 over x. Nope. I forgot the exponential there. E raised to the 3x squared minus 1 over x. And then we're going to multiply by 6x. And then this 1 over x, if we remember, we'd probably want to rewrite that as x raised to the minus 1 to kind of help us with the differentiation. So when we do the power rule on just this x raised to the minus 1, so if we were going to do our derivative there, we'd end up with negative 1 times x raised to the negative 2. And so the negative 1 that we get from power rule is going to cancel with that subtraction. It's actually going to make it addition. So we'll have plus x raised to the negative 2. And we'll just leave it like this. Now for this one, we do actually need the parentheses here because we have addition, or we had subtraction, but we do need the parentheses. So just to be careful, a lot of times with these kind of chain rule problems, we just want to make sure we're using parentheses where needed. We didn't really need the parentheses here because there was no addition or subtraction inside the parentheses, so it was all multiplication. So we could drop the parentheses. Same thing over here. We just have the 5. But this one we do need. All right, so let's try one more. Let's get a little quotient rule going here. So the next example, our function is y equal to 3e to the 2x over 1 plus x squared. And we want to differentiate this. And as this is written, what do we have? Well, we have some x terms on the top. We have some x terms on the bottom. And this is a fraction. There's a quotient here. So the first rule we got to use is quotient rule. All right. So again, let's call our derivative y prime. And the way we implement quotient rule is we write down our quotient as a product. So top function times the bottom function. And then we just do 2 copies of that. And then in the first copy, we apply the derivative to the first part. And then in the second copy, we apply it to the second part. And then we put a minus sign in the middle there. So quotient rule gets subtraction. So it's kind of like product rule. And then we make this into a big fraction, and we take our original denominator, which was 1 plus x squared, and we just square it. All right. So that's the quotient rule part. That's nothing new. Now what's new here is just doing this first derivative of the top term here. So this is an exponential, and it's not just e to the x, it's e raised to the 2x. So we're going to use our general exponential rule to help us with this. So now we're going to use our general exponential rule. So how's that going to look? Well, first, when we differentiate this, the exponential just stays exactly the same. So we're going to have 3e to the 2x. And the 3 is just a constant multiple, so it kind of sticks around there with the exponential as well. So it just looks the same. And then we take our exponent, the 2x, and we multiply by its derivative. So this is us doing the derivative of that 3e to the 2x. So we're using our general exponential rule. And then from there, everything else, though, is pretty standard. So we have our 1 plus parentheses 1 plus x squared. Then we have our minus 3e to the 2x. This one is just regular power rule, so we get 2x there. And this is all over 1 plus x squared squared. And again, with quotient rule, if you have terms being added or subtracted inside the parentheses, just leave this as squared. Don't try to do anything. All right, so then we just finished differentiating. Derivative of 2x is 2. And we're done. Now, one thing with exponentials, sometimes we can actually kind of simplify a bit. And in this case, we can do a little bit of simplifying. We can simplify this because there's a 3 in both of the terms in our numerator. There's an e to the 2x in both of our terms. And there's a factor of 2 in both of our terms. So we can actually factor out, well, 2 times 3 is 6. So we can actually factor out, put it down here, 6e to the 2x. And then what do we have left? Well, we're going to have a 1 plus x squared, and then minus just that x. So we're going to have 1 minus x plus x squared all over 1 plus x squared squared. So, this isn't really necessary to simplify here. Directions just said to differentiate. So if this was, like an exam question, just finish differentiating and that's it. But we know from experience, a lot of times we want to do stuff with our derivative. So if we wanted to figure out where this derivative was equal to 0, well, then we would want to factor it like this. All right, so we're going to practice more of these in class, and then we'll also see how the chain rule can be applied to natural log functions. So we'll see you then. Bye-bye.